Okay, well, our next speaker before coffee is Matias Zaldarriaga, and he's going to tell us about the effective theory of large-scale structure.
Thanks very much to the organizers for giving me the opportunity to speak today. So I'm presenting work with some collaborators listed here, and the original work was done also in collaboration with Daniel Baumann. So here we are after the beautiful Planck results, and there are many takeaways about these results for me. Many very interesting things that we have been discussing so far, the constraints on NS, the constraints on non-Gaussianity, the lensing constraints, or lensing measurements. All of very nice results. And then for me, there's also another takeaway, which is that pretty much the era of getting nice results from two-point functions in the linear regime is over. There's just nothing else to be done in this respect. But okay, there's polarization, sure, but this is done. And we are beginning, the nice things, we're beginning to get nicer and nicer things from higher order statistics, like, for example, the lensing reconstruction, the trispectrum of the CMB, and the bispectrum for the initial conditions. The other takeaway, obvious takeaway message is that the constraints on parameters are incredibly tight. These constraints on non-Gaussianity are incredible. Look at the local error bars. They're just incredible. So, I mean, and however, we have not gotten all the answers that we want. So we want to improve these things, and we're going to live in the regime in which we can no longer do it from just the linear theory and everything is easy. So what's going to happen in the future? So furthermore, as we know, in the future, we've heard a lot of the statistical power in the data is going to come from large-scale structure. And to beat these kind of constraints that we from Planck, we will need more and more modes. And as Uros was saying, this will push us into the nonlinear regime. So we will be trying to get very precise measurements of very interesting things and trying to push the frontier as we possibly can into the uncharted territory of the nonlinear regime. And so, so this has motivated us to try to see what we can say from not from a numerical simulation point of view, but from some more analytical point of view, about the problem of structure formation in the universe. Of course, this problem has a very long history, and for the most part, for the purpose of this talk, I will talk about a problem that has already been solved in some sense, which I'm just going to restrict myself to a problem of the universe just made of dark matter, and all of the interesting things that we've heard, many of the interesting things that we have heard in the past talks are about the fact that the universe is just not made of dark matter, and so only. However, our approach is to try to have a problem for which the answer is known and see how far we can get from there, just to build from there. So in other words, we have the answer, if you want, or have an answer for which we can run simulations, for which all the physics is understood. It's first principle, real first principle simulations. We know what we should get. We can measure whatever we want in these simulations. We can compute them and see how far we can get. Now, with the purpose of trying to understand better what's the outcome of these simulations. Can we model this in a better way? Now, maybe a lot of people in the audience just think, okay, well, understand better, who cares about understanding? I just measure in the simulation and I'm done. It's true. The one reason it's true, and it's not a good reason for me. I care about trying to understand things in an analytical way, and so because I'm giving the talk, you're kind of stuck. So that's the first answer. But I think there's another answer that I want to give to this question, which is that if you think about it a little bit more carefully, even in these situations, what we choose to measure in the simulations is still very much informed by our analytical understanding. It's true that at the end of the day, we will have to test everything probably by comparing with numerical models. But still, when we decide to measure a given statistic, and we've heard very nice examples from Uros of ratios of things, this is all all based on our analytical understanding, basically understanding what's going on. Let me give you another example of this story, which is the baryon acoustic oscillation. We've already heard in one of the other talks that one of the ways to measure the expansion history of the universe, that we think we're going to be able to do better and better with very small error bars. I don't know if this will reproduce this plot, but just very tiny error bars in the future is the baryon acoustic oscillations. And so as you know, just the same physics that imprints the acoustic peaks in the CMB creates a bump in the correlation function, say, of matter in this plot. And at around 100 megaparsecs, and the linear theory, Simon also showed this plot, a version of this kind of plot. The linear theory is giving you this line, and if you measure it in a simulation for matter, you see something different. Okay, you see, and if you do it for tracers, for halos, for galaxies, it's even more complicated. But I'm just staying away from this from a moment, and for the entire talk. But people understand where this is coming from. We now understand it, and not only we do understand it, but it's understood that this comes from motions of things created by the same wavelength modes, long wavelength modes that are in the survey volume anyway, and you're measuring them in the simulation, in the data as well. So you can try to undo this in a process called reconstruction, and people think that they can do this. They can make this peak tighter again at some level. And what it boils down to is that rather than measuring the 2-point function of the data, you're measuring a higher point statistics, combining the information from this higher point statistic to recover some of the information that is lost by making the peak broader. So it is still the case that. And then you go test this with a simulation. But in order to propose what am I going to do, as you go towards the nonlinear regime, even if you started with Gaussian initial conditions, you generate some of this information is bleeding into the higher order moments. If you want to recover this, like in this example, you need to have some analytical understanding. So I think it will be very useful to try to get this analytical understanding as best we possibly can, see where it fails, see where it fails in the simplest possible models. Let's start from there and see what happens. And then when we build up and put halos and so on, do it knowing where it already has failed or why things have already failed in the case of dark matter alone. So that's kind of the strategy. Now, for all of us cosmologists, we've known about how to do these kind of analytical calculations for a long, long time. We all do them, and what else can be done? So analytical calculations, perturbation theory, people do this all the time. They write some sort of equation. I mean, myself, everybody write some sort of equations for some fluid, some continuity equation, some force Euler equation, the Poisson equation, then expanding powers of delta, get some with some stochastic initial conditions. It appears that everything has been done, and you compute this, and you're done. And I'll try to first convince you that this is not quite the accurate situation. So I think this is what we all do, and it's very good for computing the lowest order result, so-called the tree-level result. So if you're computing the power spectrum, it's just the linear theory is great. If you go to sufficiently large scale, this is perfect. If you calculate the bispectrum, the first correction, the 3-point function, perfect. But the moment you start to compute the first nonlinear corrections to these quantities, and this is exactly what we want to do, because we want to push. We don't want to live where the nonlinearities are negligible, because then we are living in the very low case. So we see how far we can push this. And the moment you start doing that, even though we can do these calculations are not particularly good. And let me give you some examples. And by not particularly good, I'm not going to say whether it fits the simulations or not fit the simulation. Regardless of fitting the simulations, there are some conceptual issues, okay? And we should understand these conceptual issues. So what are these first nonlinear corrections? So let me give you, so let's imagine that we are computing the 2-point function, the power spectrum. The lowest term is just the linear theory power spectrum. Okay, great. So then the first order correction is try to see other scales. You're computing the power spectrum at a scale k, and you're trying to figure out what is the effect of other scales of different wave number, call it Q, on the power spectrum of the scale K. And you then add the result, the influence of all the modes of different Q on the K that you are computing. This is the so-called one-loop power spectrum. This kind of perturbation theory can be organized in some sort of Feynman diagrams or loops, and people have a one-loop calculation. It's the first non-trivial correction to linear theory in the power spectrum, two loops, blah, blah, blah. Okay? So what happens when you do that? So this is a plot of just the power spectrum of dark matter over some fiducial power spectrum. This is the result of linear theory. This is the one-loop term. This is the two-loop term. It's supposed to be some series that is getting us towards the answer, which is the dots. So if you go to the linear regime, very, very low K, everything is great. The linear theory starts working great. Supposedly, we're doing some calculation that is improving things, and one loop, two loop seems to be the same. There was some nice talk in one of the parallel sessions. Some brave soul computed the three loops and was showing the results, and it's just as big. And even if you go to low K, it even gets bigger than all of this. So what are we doing? What's going on? Why are we so happy about this situation? Now, it's even a little bit sad, because you may say, okay, forget about it. These are such high Ks that perturbation theory, there's no information there. It's just like, it's giving nonsense because it's just impossible to compute anything on those scales. Now, however, let's choose something very simple. Let's just take a numerical simulation and take those initial conditions and predict the position of particles, or just using the Zaldarriaga approximation, which is linear theory in this Lagrangian space, and compute the correlation coefficient between the answer of the full numerical simulation and the Zaldarriaga approximation. This is this curve. So at K of 0.2, and if you do it, you can do it with second order perturbations theory and so on. So at K of 0.2, which is the one that where this is apparently giving nothing, the phases of all of these modes are great. I mean, it's the correlations of 99%, things like this. So it's not that the information is not there. Somehow, and somehow we are not able to combine these terms, or something is going on, because the correlation coefficient is very good. However, the amplitude is terrible, and if you compute anyway, so something is, okay, but let me even give you some other more conceptual problem. So if you compute these perturbation theory calculations, there's nothing in this calculation that tells you that it's only valid for lambda CDM. It's something you can do for any universe. So let's just play around. In fact, why don't we play around with the simplest possible models that people have talked in the very, very beginning? Einstein de Sitter models, okay. Omega equals 1, power law initial conditions, okay? This is the simplest, okay? It has no scale, everything. The only scale, length scale is the nonlinear scale. Great, so everything has to be a power of k over k nonlinear. Let's do the calculation as a function of n, see what happens. So what you discover is that even this one loop calculation, if the n is the slope of the primordial power spectrum, if n is not in the range between -3 and 1, the results diverge. So you don't get nothing. It's a nonsensical answer, okay? Not only that, it's not that, but on the other hand, say take n equals -1. You just run the simulation, call your friend, or go to the archive. It's just some curve. It's nothing special, okay? There's nothing going on. So how come, what's going on? How is it possible that there's no red flag, the recipe says do this, do that, and you get a nonsense, but it's nothing bad in the simulation. It's just a standard thing. Furthermore, you can say, okay, who cares? I mean, for our universe around the nonlinear scale, n is equal to -1 point something, -1.5. It lives in this range. It's okay. Forget about it. Just do it and just forget about it. But if you do 2 loops, this range here of acceptable n's shrinks. If you do 3 loops, it shrinks again. If you do, there always comes if you do a power law, there always comes some n in which it diverges. So clearly we're missing something, we're doing something wrong, okay? So if we are going into this era in which we want to compute everything to 1%, shouldn't we be able to do it in the case where we know the answer, and even if it's the simple answer, okay? So that is what I would claim is the state of the situation, and we were not so happy with this situation, even though this looks like an academic problem. And so And so, so we started to try to see what is missing, okay? So we would want to have a way of computing things in which we'd get an answer for any n, and it's just an answer, and hopefully it fits the numerical simulations, okay? But first, let's try to get an answer. But what is happening? What is happening is very clear. So perturbation theory is supposed to be able to calculate things on large scales, not on the very small scale. So there's some scales, some magic scale related to the nonlinear scale in which perturbation theory is just not applicable anymore. Okay. Now, when you are computing these loop calculations, you're doing an integral over the effects of every scale on the scale of interest. And you're also including the effects of these scales in which perturbation theory is not giving the right answer. In particular, for some of these models, the perturbation theory is giving an infinitely wrong answer for these modes. Okay? So your answer is nonsensical. But the problem is that this part is not to be trusted. This is not something that you should be included. You can include because it's not something that you're computing correctly. So this is the source of the problem. Now, if you realize, so what do you do about it? So you just relax and accept this problem. And this means that there are certain parts of, there are some effects from the small scales on the large scales that you just cannot compute. Perturbation theory will not be able to compute it. This means that if you want to have something that makes sense, it will have some free parameters that will encode the part of the calculation where, perturbation theory assumes single stream, and there's not a single stream, and so it's not giving the right answer. And so, this will need to come from somewhere else. It should come, say, from a numerical simulation, or from the data, or from different statistics, or something like that. So in the old paper we had tried to write down a theory that consistently accounted for the lack of knowledge of the small scales directly in Eulerian space, and for reasons that, if I have time, I will motivate at the end. We've been trying to do it in Lagrangian space related to the BAO. The reasons are related to the BAO. So what is the story? So what is happening? I think this is very easy to understand what you need to do, and the goal then would be to have a way of calculating, and you get an answer that is finite and that at least is finite. Let's just start with that. So clearly the issue is that we do not want to follow the details on the very small scales. We only want to follow details on large scales. So let's start by doing the following. Take the initial conditions and take some little regions and try to follow these regions, just their centers of mass, how they move. But now they have to be regions of some size, because I don't have a way, perturbation theory is not allowing me to compute anything on very small scales. So I just get around this problem by considering regions of a given size. And they evolve, they have some shapes, they move around. So clearly, if I'm following objects which have some size, the way they move around and the gravity they create is not the one of point particles. Because if they have a size, and for example, if they have a quadrupole moment, they will create gravity slightly different. They will move around in a slightly different way. So if we are talking about now a theory of extended objects, this theory of extended objects will be characterized by the multiple moments. Okay. So at the end of the day, this theory of this perturbation theory, this effective theory that we're talking about, is just saying that we have to live with the fact that we have to take some little regions, and these regions are extended, and so they have some size, and they're finite size effects. And our goal was to characterize the sizes of these some finite size effects of which you cannot compute in perturbation theory, but you can characterize, or you can somehow have a handle on them. And that's so the question is how, if you want to follow the dynamics and get an answer with a given precision, how many multiples of these regions you need to keep, what properties of how these multiples behave do you need to know. And because you are computing correlation functions, the bottom line is that what you care about is the response, how the quadrupole of a region depends on the fact that there's an overdensity somewhere else. So if there is an overdensity, a large wavelength mode, the quadrupole, how it deforms. So that's a parameter that is outside what we can compute from the perturbation theory. And you need to know this to the, okay, in principle, you need to know the quadrupole, the octupole, and so on. But imagine that you just want to do a calculation that is valid up to the equivalent of 2 loops. And in that case, you only need the quadrupole, and you only need to know the quadrupole at the lowest possible order, so how it responds to the linear density field. So there's one, for that kind of calculation, there's just one free parameter. So in general, what you want is to describe the motions of objects that have a shape. They have a quadrupole moment, so their force, the way they move, depends on the gradients of the potential, but also on their quadrupole moment. I mean, this is just standard. The way they source gravity is also through their quadrupole moments. And as I was saying about the quadrupole moments, all you need to know is kind of the response of these quadrupole moments to the faraway tides. And because you only need to know them, at this order, you only need to know the linear response, or how the quadrupole responds to the linear. Then basically, you write down the most general response of a quadrupole, and it has this one parameter, which is the free parameter. But so the bottom line is that at least in this, at least if you think that what you're doing is just following objects, so okay, and what would be? Let me just say one more thing. This splitting of the initial conditions into objects of a given size was just my invention. So clearly, the answer of the numerical simulation cannot depend on how I split these things. So I would want to get a way of getting an answer that is finite, that is independent of this, so I would and well defined. And all of this is possible, and is kind of some equivalent to some renormalization kind of procedure. But at the bottom line then is that if you're following up to, and you care just say up to 2 loops only, there's only one parameter that enters. So these are the people familiar with perturbation theory would recognize these 2 equations, the standard equations. If I had put 0 here, it would be the standard equation of Lagrangian perturbation theory. At this order, you need to add this additional term. That's the claim. Okay. And the bottom line, what's happening is that the reason that perturbation theory sometimes is given infinite answers is because you are computing this S is the displacement field. You're computing the square of the displacement at a given point. So if you have the RMS displacement at the same point, and this in these models where n where there are divergences, this quantity diverges. But what you get when you do this is in reality this just changes to the quadrupole moment of the mass distribution, which is the sum of the quadrupole moments due to the motion plus the quadrupole moment of these individual big objects. And so this is the full quadrupole moment of the mass distribution. So as you change this smoothing, you're just changing what you are assigning to the motions of the centers of mass compared to the sizes of the individual objects. So this answer is clear. You can show it's independent of the smoothing. It can be made finite and so on. And it can be made finite because now, in addition to, for example, at one loop, in addition to the 2 standard terms of perturbation theory, there's an additional term coming from this additional quadrupole response force that has the exact right properties as a function of k and so on to cancel. So it's the non-trivial check is that this term has the exact same k dependence as the divergent, the bad pieces that you get, and you can fix it in this way in a renormalization type. So the bottom line is that I mean in something like this, you especially if you're talking about scaling universes, which is the very simple case. In that case, you know there's nowhere to hide. You know exactly these terms, how they depend on everything is a function of k over k nonlinear. You know exactly all of these terms, how big they are relative to one another, and you know, for example, if you consider a scaling universe with a spectral index similar to the one of the nonlinear scaling universe, what you discover is that the biggest correction is the standard one-loop correction of standard perturbation theory, but only down by a square root of k over k nonlinear is this quadrupole response term. Then there comes the two loops. So you should never do a two-loop calculation without including this term, which is bigger. And then there's other terms that you can keep including. And the other bottom line is that if you just care about computing the power spectrum, these rules tell you that if you just care about computing the power spectrum of the density fluctuations up to less than 3 loops, because 3 loops is too complicated. Well, somebody has already done it, but okay, for me it was too complicated. There's only one parameter that you need to fit. So this is not my work. I'm just here flashing some transparencies that Leonardo Senatore gave me just to give you some ideas. So he has been trying to do this in fitting to some simulations. So it's again showing the same kind of plot of P over some fiducial P. The linear theory is this green curve, one loop, the standard calculation, two loop, that is much, this thing that looks like it doesn't converge. And he gets one parameter to fit, so this has one parameter fits, but this is the result for one loop that you can say, okay, it's much better because it has fitted one parameter, but then the two loop term even gets better, contrary to what happens here, and it has no additional free parameters. So I don't know, this needs to be done more carefully. The other thing that I want to stress with this is that all of these calculations come with error bars, so it's not that you make a calculation and you compare to the simulation, and when it doesn't work, okay, that's where it fails. No, you need to be able to tell me in advance where this should fail. This is the test that you're understanding what's going on, okay? So these calculations come with error bars. I mean, according to him, these are you know in the series what are the next terms, and he plotted them, and the place where this starts to fail is exactly the place where one of these terms is getting big. So it's nothing appears out of the ordinary. So it appears to be. Okay, I would say some general lessons from this EFT is that the small scale dynamics is something that is not captured by perturbation theory. This is the source of these problems. You have to live with that. You will have to get, but these mistakes have very characteristic sizes that you can estimate and scale dependencies. So you know how many more terms or the errors, you know things about those terms. It's not that it's a free for all. If you're just doing a calculation up to a given precision, there's only a small number of parameters, in this case up to 2 loops, which is kind of only one. The calculations come with attached error bars. And the other thing that I wanted to mention is that we're not really strangers to this fact that the small scales we need to model in some way. And this is exactly the same we're doing with bias, okay? So, and basically, we're just at the end of the day, we have to write the most general parameterization of the bias. For the dark matter, we have a little bit more handle on the kind of terms that you can write and how big they can be. But again, there's the same kind of story. So let me just spend the last couple of minutes telling you about the reason why we started to do this we had done this in Eulerian space, and I gave you the version of it in Lagrangian space. And the reason we were doing this is because there's another issue with this. This is not a big deal, but this loop expansion that we typically do and compute at a given order is just counting the different terms in powers of how many power spectrum they have. Linear theory has one loop is something proportional to power spectrum square, 2-loop power spectrum cube, okay? But however, living inside of this power spectrum square, power spectrum cube terms, there are terms of very different sizes. So these are really a bad organization of the of the of the calculation. We think we're doing something that each term, but it's, I mean, inside of there are big terms and small terms, and to the extent that some of the big terms we want to sum up to many loops, but the small terms you don't really care. An example of this is that inside of the one loop lives, so if you want the correlation function and the BAO scale, obviously, for example, you would say that if you want a 100 megaparsec region, it can have an overdensity or another density whose typical RMS fluctuations has to do with the correlation function on a 100 megaparsec scale. This is 10 to minus 3. So that kind of effect is a 0.1% effect at the BAO scale. But obviously, the effect, the nonlinear effect, is much bigger than 0.1%. So this is not the main term. There's another term, which is this motion. So, and this happens at every order. There's these wildly different sizes of terms that we are counting as if they were the same, but they are not the same. And in particular, in Lagrangian perturbation theory, some of these terms, the biggest ones, the one of these motions that have nothing to do with any dynamics, they're already added up to higher orders. So that's the reason to try to do this in Lagrangian space. In particular, if you look at perturbation theory, if you look, for example, at one loop, it's not there are different combinations of the power spectrum that enter. So it's the motions, P of Q over Q squared is motions, is the lengths of motions. These produce, if you're interested in a mode of scale K, is the motions produced by wavelengths longer than K. There's the motions produced by wavelengths shorter than the K that you're interested in. There's the density fluctuations from modes larger, from modes smaller. This one really doesn't enter, but these three all enter somewhere. And they're not the same, and this is a plot of them just to make the point. So, I mean, they have, you know, quite different sizes. And so to attain a given precision, in particular this one that has to do with the motions from the larger scales, you want to add more than the other ones. And this is pretty clear in these nice cartoons of the BAO, the widening of the peak, where you see that it's very coherent fluctuations of this ring that are moving things around, okay, and making the peak wider. And then it's really these motions and not the overdensity that on the 100 megapart produced by these modes that you care about. And is Lagrangian perturbation theory is just taking that into account automatically to all orders. And so if you start there, you're already pretty close to the answer, and that's just the motivation. So let me conclude by saying that I think there's substantial room for improvement in our modeling of the mildly nonlinear regime, even for dark matter, even in the simplest possible cases. I know this is a very academic problem. I know people will think I don't care, I just do okay, fine, but I do care. I would like to get, understand this the best possibly can, make sure that we can have these and know exactly where the nonlinear scale is, where things are really breaking, because they're clearly not breaking when delta is equal to 1. For example, in our universe, things go nicer even further. And have, as much possible control. And then, yeah, I appreciate the fact that the most interesting things are halos and redshift space distortions, and we'll get there, but we need some more time. Okay, thank you.
Thanks, Matias. Questions?
Perhaps, I'm sure you know this. In effective field theory approach, there are two scales. One is your infrared, where constantly the super Hubble modes are entering into my Hubble, inside my Hubble radius. And the other is your, of course, this UV mode where you're saying the lambda. Now, the infrared part is very much time dependent, and on the other hand, the UV part is more like, I mean, it has both time as well as spatial dependence. So how do you take care of that?
The IR effects, the IR modes do not. So, for example, if you just look at correlation function of a given scale, modes that are much longer to this scale, this motion that moves everybody coherently just by Galilean invariance doesn't do anything. And so when you do this loop calculation, Galilean invariance already,
This is not true for warm dark matter, for instance.
well, yes, I agree with this, but I'm starting with the problem that I know the
I
answer.
know.
Okay, so it's true. If you have a relativistic thing that moves a lot, then we will have to modify this. Okay, sure.
I mean, how do you? Okay.
But the real IR is going to be convergent anyway, even for warm dark matter. But anyway.
Take one final question at the back.
Hey, Matias, I actually have two questions, hope it's okay. One question is, the parameter that you introduce is a function of time.
Yes.
Is it possible
Well,
to
yeah.
guess the time dependence to make it easier to use?
That's the first question.
That's the first question.
In the case of a scaling universe, of course, you know exactly the scale dependence. In the case of our universe, we don't know the scale dependence. A guess is that it's the same scale dependence as, similar at least, to the scale dependence of a scaling universe with the slope around the nonlinear regime. This is something we need to investigate further.
The other question is from your Lagrangian equation of motion. It looks like that parameter looks like sound speed.
Yeah,
And
that's the reason it was called sound speed in the other paper.
right. Now, you...
But it's really, I mean, it's really the quadruple. I think this is much nicer.
Right. On the other hand, on the other hand, you motivate using the quadruple, which suggests that somehow I should worry about the anisotropic part of the stress, which seems to introduce not just sound speed but other parameters.
Yeah. Okay. So the thing to say is that what enters is the quadrupole, and this I gave you the formula for the trace-free part, but there's also the trace. So, but all these terms combine into this one parameter if you care just about the density. And so I skipped the part that if you were to measure other things than the density, and let me mention one thing, that this parameter, for example, you can get it also from, is nothing other than if you were to measure in a simulation the 3-point function of the displacement with 2 points very close to one another and one far away as a function of distance. From there, you get all of these parameters. So that's another way of doing it, regardless of the power spectrum. So that's what these things are. And then you can see that there's more than one parameter because of the tensor structure and so on. I just skipped a little bit this time.
Good. Well, before we break for coffee, let's just thank Matias again.